Yeah, thanks for having me. I'm going to talk about something today that I'm passionate about. So first, who am I? I'm Cyrill. I work as a core dev in Parity, specifically in the contracts team. And I do mainly compiler work, but also a bunch of other stuff, like all things contracts. And so what I will be talking today is about contracts on Polkadot. So as you may know or not know, we are building an entirely new contract stack based on RISC-V. And I will talk about that. But first, just to make sure to bring everybody on the same page, I will also briefly talk about Polkadot architecture basics. And in the end, I will show a brief demo of what you can do with contracts, or rather, yeah, how to deploy it, and something you can do, something interesting. Okay, so to explain this, I think we have like four puzzle pieces when we want to have contracts on a blockchain, right? So we will first need a blockchain, and then we will need some runtime to help contract execution. Then we need a virtual machine to run the contracts code, and then we also need a Solidity compiler if we want to support Solidity, but not like deploying PolkaVM. And so this will look more or less like this. So I will guide you through this. So on the left, we will have the contract code, then we compile this into some contract blob, and then we interact with a blockchain to like execute the contract on the right. So let me first start with the blockchain, or with Polkadot Hub, because this is all about like contracts on Polkadot or on the Polkadot Hub. So let's unpack this, what this means. So we are starting off here on the far right. And by the way, we will work a bit, we start on the top and we'll work our way down to the lowest level. So Polkadot is a bit unlike other blockchains, if you think about the Ethereum L1 or Solana, because Polkadot is really a network of parachains or an ecosystem. And when people talk about Polkadot, they either mean like the ecosystem or the relay chain or the network. And all of this is like a bit unlike other networks, right? When you talk about Ethereum, like you can also mean the ecosystem, but mainly when you say you deploy a contract on Ethereum, what you mean is like either on a rollup, but you would default to think that you would deploy to Ethereum the mainnet, like the layer one, the Ethereum network itself. And Polkadot works a bit different. So in Polkadot, everything is a parachain except for the relay chain. And we will get into what this means, but first, parachains. So I think this was like confusing historically for a lot of people, but if you're not familiar, if you're more familiar with how Ethereum works, just think of them as rollups. So parachain are more, I mean, this is technically not correct, but they are rollups, some sort of rollups. Our security layer for those rollups is called the ELF protocol. If you're interested, I have a link here in the slides. But the essence is the parachain node is the collator, and the relay chain node is called the validator. And so the parachain collator produces a validity proof of the relay of the parachain block. It's called, and then it sends this to the relay chain, to the Polkadot relay chain validators, and they have this proof of validity function, and they sort of re-execute and prove the correctness of the parachain block. And this is how our roll-up model looks like, more or less. Are there any questions so far? I'm trying this to
There's
keep
various. There's various. Would you prefer to read them yourself, Cyrill? Do you want me to read them? What would make your life easiest? It could be a little bit difficult sometimes with the sharing screen and the reading questions at the same time.
I can read them, but I see a lot of hey messages.
Yes, I'm going to make your life easy. First question, do all the various EVM tools work within Polkadot?
So natively, none of the EVM tools do work in Polkadot. Oh, something happened.
That's okay.
I misclicked, sorry for that.
That's all right. That's why we're here.
But you still do see my...
Yeah, I see
screen, right?
full screen ahead.
Okay. So first of all, like, no, the EVM tools, or like how you would interact with an EVM chain, is like vastly different how you interact with like a parachain with a relay chain node. However, you can emulate certain things, and we will see this later on. And then some tools might work because the Parachain takes care of being compatible enough. Does that make sense?
Yeah. And then various questions, one around, is the EVM a roll-up itself, and how does this affect sort of EVM-focused parachains?
Okay, so with EVM rollup, I mean, you could have a CK rollup or an optimistic rollup being verified by a Polkadot validator. It's just like the ELSE protocol, so how parachains work today is like much more efficient. So I think that's why no one do this. What you can do, however, you can have a parachain that ships the EVM, and then it more or less looks like an EVM rollup because it's like exactly some blockchain that is like very, very compatible with Ethereum, right? There's only like very few minor differences, and it's just sort of rolls up to Polkadot instead of the Ethereum layer 1.
Nice. I think let's continue. Let's not slow it down. Keep going, sir.
Great. So what we see, there's no contracts on the relay chain. So the idea is like the relay chain, the only thing this does is like what you see here. It like validates those validity proofs from the Parachain. It only takes care of like providing security to the network and passing messages, like some sort of connecting the parachains all together. And so this means there's no contracts on the relay chain, because that, like everything or almost everything else, should be done by a parachain, right? And so what we see is this like pattern of dApp chains. So when everything is a parachain, like, yes, you can have contract chains, like someone asked before about the EVM. So you can have like EVM parachains. So I'm not going to name anyone here, so as to be fair, but maybe you recognize some logos on the right. But what you also will see, like, there's a lot of those dApp chains, which means like a single dApp that would be a contract on Ethereum or on Solana is actually its own blockchain on Polkadot. So you can have a DEX chain that's like the entire chain is only a DEX, right? So maybe you know Uniswap from like the Ethereum ecosystem. So they kind of made this too. So because having your own blockchain, if you're a big enough dApp, is kind of powerful. The downside is it's like much more work, and it's like writing a contract is also much simpler. It makes interaction with like other things, that like other contracts, easier. So I don't think there's a clear-cut answer like to what is better. Like I guess it depends on your use case whether you should do a dApp chain or a contract chain. The problem is, so far on Polkadot, like everything is a parachain, and there's no contracts on the relay chain. So either you have to choose a contract chain to deploy your dApp, which also has implications, or you just write the dApp chain. And then one thing I kind of need to talk about, it's like another slightly technical term. So there are system parachains or system chains, as we call them. So typically dApp chains are like, they run business logic, like DEPs is mostly only business logic, but there's also like core, like very intrinsic functionality to the blockchain, right? Like issuing assets or doing balance transfers or bridging to other network. And with bridging here, I mean bridging to other blockchain networks, because bridging within parachains is kind of easy and built into the network, but bridging to other chains, governance, like dot staking, all these things that more or less touch the entire ecosystem and are like very core to the Polkadot protocol, they should live somewhere. And so this is what we call system parachains. They take care of like such functionality. They're governed by the Polkadot Technical Fellowship. So the Technical Fellowship is a DAO, and they're like technical experts that approve on runtime upgrades of the Polkadot network, for example. And so system chains also use DOT as their native token. So any parachain can have any token as their like native fee payment token as they wish. They can also use DOT, and so system chains always will just use DOT as their native payment token. And I mean, on the lowest level, system chains are just parachains. There's just like, when we talk about system chains, like you should know the difference, which is really like on a more high level than just purely technical difference. So now, what's the minimal relay chain vision? So the minimal relay chain vision is taking balances, staking, and governance, amongst maybe other things, off from the relay chain and migrating this to like either their own system chains or to one system chain. And so the thing is, first there was the relay chain, right? And so it just happened that some things were first implemented on the relay chain because it's more work to do on the parachain, and parachains launched later. So, and then it's like, I think it's just a theory versus practice thing. So in theory, like you have this perfectly scalable system, and like not the relay chain is really just the relay chain providing security. In practice, we are still having some things like balances, staking, and governance on the relay chain. But we are migrating those off the relay chain to the Asset Hub system chain. So Asset Hub is a system chain for asset issuance, and we are kind of implementing this minimal relay chain vision. I mean, it was more or less envisioned to have like a minimum relay chain from the beginning on, and this now comes into fruition. What we also do is we add contracts to Asset Hub. And so there's many terms. You hear like Polkadot, the Polkadot Hub, Plaza, the Plaza upgrade, Asset Hub. And this is what it really boils down to. We are moving functionality out from the relay chain into Asset Hub. And we are also adding contracts to Asset Hub. And this together is what we call the Plaza upgrade. So in Ethereum, they always have like, I think, cities names for their upgrades. So you can think of more or less like this. We just call it the Plaza upgrade. And so this turns the Asset Hub chain on a high level into the Polkadot Hub. And Plaza, it's called because it then becomes like this one central thing. Like if you have a city, so if you imagine Polkadot as this interconnected network like a city, then you have like the Plaza where like you go to do things like whatever, you meet other citizens there. It's just not a very specific place, but like a place with many things. So that's I guess why it's called Plaza. And I mean, it was a blog post by Rob Habermeyer coined that term. So here is again mostly what I just said. So why not just call Asset Hub Polkadot then, or rename the chain? Asset Hub was already renamed once, and we decided we technically leave the term Asset Hub because it's already a bit confusing, right? When you say Polkadot, it highly depends on the context. Do you mean Polkadot, the network or the ecosystem? Do you mean the relay chain? And now if we would also have Polkadot referring to Asset Hub, it gets like even more confusing. So we just say Polkadot Hub for this concept of this like central chain where everything lives that doesn't really fit into a dedicated system chain. So what we also do, just having contracts is not very exciting by itself, right? If we want to have these contracts actually interact with core protocol features. And so it doesn't say on the slide, but what we call modules, palettes. So there's many palettes in that will be on Asset Hub. There's a staking palette, an asset palette, a referenda palette, and these are really just modules. This is like how the substrate framework which Polkadot is built on is composing functionality. And what we will do is we will expose the APIs of those palettes as precompiled contracts. Because in Solidity, you only really have one way to extend Solidity with other functionality that it's like it's not really aware of. And so you can imagine that there will be a custom precompile, like a specific contract address. And when you call into this contract address, then it's actually, you can make referenda, so interacting with the Polkadot governance, or you can stake or unstake your dots via a precompile address. And of course, those will, so in Substrate, you have scale encoding and so on, but we don't want this for contracts. We want those precompiles to understand just the Solidity API. So you will have a Solidity interface, and then you know, like, on behind this precompile address, there's a staking palette, and this is the Solidity interface it will understand. And what's the consequence of this? The consequences is it makes Polkadot fully permissionless. You don't, and synchronously compose, and it adds synchronous composability. And this is kind of nice because deploying a Parachain doesn't give you synchronous composability with like other things, only the things that are in your Parachain, but this creates a lot of friction. And of course, contract deployment is fully permissionless. So it should make it should make that development on Polkadot much more convenient than it is now. Of course, we're not deprecating Parachains or anything. It's just another option. Okay, and then like these precompiles, these custom precompiles, we're working on them. Like they're not yet available on the test network. Hopefully soon. So again, as a summary, we move functionality off from the relay chain into the Asset Hub system chain, also add contracts. And this we call the Polkadot Hub. And in essence, it makes Polkadot look a lot like any other layer 1 blockchain, right? Because it will, if you have Ethereum or Solana where you can just go and deploy a contract if you want to have a dApp and you don't need your own chain, like this is then possible on Polkadot too. Are there any questions so far?
Quite a few, but I don't know how much you want to take them now, Cyrill.
Let's do them now. Nice. We can take 3 now, maybe.
Take 3, right? I have some responsibility. Wario asks, at the moment, which core or protocol palettes can I call from a Solidity contract?
At the moment, none, because we are still figuring out the precompile interface.
Okay, very good. How can I transfer assets between the asset hub and other parachains or external networks?
So in general, for this, you use something which we call XCM. So the cross-chain, cross-consensus messaging, I think it's called. I'm not a protocol engineer, but it's called XCM, and it enables exactly that, like communication across chains. And right now, so there's a palette, but what we will do, we will also have precompile contract addresses and interfaces, which then like abstract this for you. So and if you want to do this low level, you will have to interact with XCM, which will be also possible if we are most likely going to expose like the underlying interface on a low level too.
Okay, good. Is there documentation for the precompile? There's lots of precompile questions. Is there documentation for the precompiles?
Not yet, because as I said, they are not yet ready, but should hopefully be very soon deployed on the testnet.
Good, right. Let's keep going. Brad is also in the chat. I think he's going to try and save your day. So let's keep on at it.
Sure. What I recommend for now, if you try to do something with a precompile, it's a bit difficult, but you might just have to mock it or just assume there's a precompile where you can send messages. And if in doubt, like in the end, there will be links to various support channels, like, and you can also just ask like, hey, will this be possible? Does this make sense? Until like the actual interfaces are available to check out.
Cool, let's keep at it.
Okay, now we have defined our blockchain and we know like what we talk about when we say the Polkadot hub. And let's go a bit lower level and talk about how we achieve like Ethereum compatibility on our blockchain. So what we want is an EVM-like runtime API. So we are deploying RISC-V based contracts, which I will talk a bit more like in a later slide why we are doing this. But for now, the idea is that we want to provide an environment to contracts and contract developers that looks a lot like the EVM APIs and in general the Ethereum environment, right? But it doesn't matter what's like actually executing the contracts under the hood or what bytecode they are, as long as we provide the correct APIs. And of course, we need things like contract storage and sandboxing, because contracts are untrusted code, right? And the palette is implementing this. Then we will, as I said, PolkaVM is a RISC-V based virtual machine that supports like any language. And of course, like Palette Revive will make sure to invoke PolkaVM to actually execute your contracts. And it also provides a bit general Ethereum compatibility layers. So for example, like all the RPC interfaces and transaction receipts. And also, so we have the problem that substrate accounts, which is again the framework Polkadot is built on, uses like different cryptography schemes for their accounts. And so like it boils down to, so Ethereum addresses are 20 bytes and substrate accounts, at least on the asset hub, they are 32 bytes. So, and they are not compatible, but we still want to your users be able to use whatever Ethereum wallet they have. So we kind of have to make sure the palette or our blockchain through the palette understands like both accounts. So thankfully Polkadot has beautiful account abstraction from the beginning, so we can do this. It's just not trivial and it needs to be implemented somewhere. So the palette provides an account mapping where you can like map Ethereum addresses to substrate accounts and vice versa. This is like because you kind of want to be able to use either an Ethereum account or a Polkadot native account. And this requires some supporting code. Any questions?
No extra ones at this stage. You can keep going, sir.
So PolkaVM, what's executing the contracts? So a bit of history, and then also why we are doing this. So almost 3 years ago, or 2.5 years ago, our tech leads started to explore alternatives to WebAssembly. So our Parachain runtime functions are implemented, use WebAssembly. And we also had a contracts palette that used WebAssembly. We hit kind of fundamental limitations of WebAssembly. We will see soon why. And then sort of the idea was born like, hey, can we not use just RISC-V as our contract format? Then Jan wrote a proof of concept PolkaVM implementation, which showed amazing benchmark results. Given it was just a POC, this was like a proof of concept. This was like really mind blowing. Then meanwhile, since PolkaVM is also solves some determinism issues of WebAssembly, the idea of jam was sort of born around discussions around PolkaVM. And then it went on, and last summer, the referenda passed to enable PVM contracts on Asset Hub. And now we are doing this. Now we are implementing this. So why not WebAssembly? So WebAssembly is praised as like a faster alternative to, is often praised as a faster alternative to EVM, right? It's also, it has good adoption, especially in the Web 2 world. There's also a lot of blockchains having WebAssembly contracts. But it turns out, if you look closely, it's actually not a solid choice for blockchains. Why not? Mainly for contracts, the problem is WebAssembly, despite its name assembly, contains actually stuff like higher level control flow elements, like loops, for example. And it's also stack machine, but we're compiling contracts. In the end, we're executing them on a register machine. So the compiler, interpreter, whatever, has to deal with, for example, register allocations. So this is an NP complete problem. So it's like a very, very difficult problem to solve. And we rather don't want to do this on chain, because contracts, unlike web applications, are very short-lived programs. And think about it, one transaction can have many contracts in the call stack. You can first go through a proxy contract and then like maybe take a loan and then call a DEX. So if you need to compile every contract in the stack, and this takes you a long time, this is very problematic. And what you will observe is that often, because those contracts, they don't really do a lot of work most of the time, so it doesn't really matter whether they're slow or they're doing a lot of work in precompiles anyways. So what you will observe is that by the time your WebAssembly contracts have finished compiling and you start actually executing the contract, like the EVM would have executed the same contract like dozens of times or even 100 of times. And this is really bad because no matter how much faster WebAssembly is, like in practice, WebAssembly just loses hard in the average contract case. Okay, why we're not deploying EVM? EVM is also not very fast, so it's also not a general purpose VM, and this basically means it leads to very slow contracts written in obscure and domain specific languages, which kind of limits what you can do with contracts, and we want to innovate and remove some limitations in this space. So meet PolkaVM. PolkaVM is a RISC-V based general purpose virtual machine. RISC-V based means it's a register machine, and its instruction set architecture looks like a lot like RISC-V. We made minor modifications to it, mainly to make it more on-chain friendly, and it supports the RISC-V embedded instruction set architecture. And so what you do is you just compile your programs to the CPU, and then our linker translates it into a PVM blob that then is executable by palette revive. PolkaVM provides very efficient compilation because RISC-V is very close to x86 bytecodes. So all those hard, annoying problems, compilation problems that we have with WebAssembly, they actually just don't exist. So we can compile those programs much faster. And it also means that we can let LLVM or whatever good compiler framework spend a lot of time off-chain producing like very, very optimized blobs. So this means we have like very efficient compilation, and the contracts we are execute are actually like very optimized and fast. And yeah, PolkaVM also has gas metering with a gas model suitable for contracts, which not all WebAssembly implementations have. So as it is a standard, if you have portable code, for example, JVM or also nodes like the V8 engine does this, you can actually either interpret or JIT compile the PVM blob. Interpreting it means you can start execution instantly like the EVM does. So interpretation is obviously also much slower, but it might not matter because, as I said before, if your contract does not do a lot of work, like interpreting it will always be faster than compilation. But if you also can compile your contracts, yes, you pay a fixed upfront overhead, but after compilation, your code executes much, much, much faster. It executes in near native code speed, and with this, I mean actually near native speed, not as we'll see in some benchmarks. And contracts on Polkadot Hub will support both. We just start with the interpreter, and the JIT compiler will follow later. So what this translates is more or less whether to use the interpreter or the compiler is kind of an optimization problem. So if you don't have a lot of iterations, as you see on the bottom left, you might want to use the interpreter because that's faster. But the more iterations your code does, so if you imagine something like calculating Fibonacci numbers or calculating a hash, then like the more iterations you have, eventually will reach a tipping point where it might be worth to use the compiler. And here are some benchmarks. So what this does is it executes a NES emulator, and so we can compile this. It's called Pinky, and we can compile this Pinky NES emulator to various virtual machines. So we have the PolkaVM recompiler, the PolkaVM interpreter, Solana RBPF, and WASMI. WASMI is like what the old contracts, the WebAssembly-based contracts palette uses. And we also have WASM time here, which is what Parachain validation function uses. It's like the state-of-the-art WebAssembly compiler, the state-of-the-art WebAssembly implementation. And what we see here is like just what I said before, the recompiler, it has a bit of compilation time, but its execution times are like very, very fast. So WebAssembly WASM time is considered to be like top-notch standard, like the best of the best compilers for WebAssembly. And PolkaVM, and this is not even like very well optimized, it just executes this interpreter faster than the fastest WebAssembly compiler. And then what we also see is the interpreter, while it executes a lot slower, it has zero compilation time overhead. So there's nothing missing here. It just doesn't show up because it instantly starts executing contract code, which is again very beneficial if you just, for example, do a token swap, which executes dozens of instruction or hundreds of instruction, then you probably want this. And then we see like existing solutions, Solana and WebAssembly contracts. So they don't really excel in neither metrics, right? So their compilation time is like quite high, but also their execution time isn't very something to brag about. And with PolkaVM, we can basically have best of both worlds. So what this does, this unlocks new use cases that are so far not really possible. But so you can just, instead of a parachain, write your code as a contract once the JIT compiler is available, because it will execute around the same time as your native WebAssembly code. If startup overheads feasible for you. You can also have interpreter contracts for other languages. So we might as well see Python or JavaScript, or like, Move or Solana contracts on Polkadot top. And if you, let's say you want to verify a Stark proof, and then what you do on Ethereum, you always have those recursive snarks, because there's basically there's very few curves, and so very few verifiers that actually work on chain. And then you always have to verify your proofs recursively, and this limitation should just go away with contracts using PolkaVM. Any questions?
Rada's done a very good job of handling them, so you can keep going.
All right, very good or terribly. Okay, so let's see. Now we also want to support Solidity, but we don't have the EVM, right? So we want to support like existing toolings and libraries and wallets and everything, but we don't deploy the EVM. So what we do is we just compile Solidity down to PolkaVM, and together with like the Ethereum compatibility of the palette, we kind of have something that from the outside it looks like it would be an EVM, but it isn't. This comes at the cost of decreased compatibility. It's not terrible, so most common things still work fine. And we have in our documentation, there's a list of like what's not supported. And also, if you're familiar with, for example, zk-sync, they kind of do the same. I mean, on a conceptual level, they do something very similar with their CKVM. And so our Solidity compiler, it uses Solc as the Solidity front end. And then it asks Solc to compile the Solidity contracts to Yule, which is the intermediate representation the Solc compiler uses internally. This is nice because it allows us to not actually write the Solidity front end, which is kind of difficult because it's a moving target, breaking all the time. There is no spec, but Yule has a spec, and we just also preserve the semantics by using Solc as our front end. And then we translate Yule to LLVM, and then we ask LLVM to optimize it, and then we turn it into a PolkaVM blob. And it looks more or less like this. So we go from Solc to Yule, and then the Revive compiler translates this into LLVM, which optimizes it, and then the PVM linker links it. And this is all off-chain. So we're quite flexible in the optimizations we can apply. All right. Any questions regarding the compiler?
So bits about PVM. There's one about for the interpreter. Does it mean that the contracts are stored on the blockchain raw, i.e. the way they're written by the developer?
Yeah, I can take 2 questions and then we can move on.
That was the question. Does it mean for the interpreter? Does it mean that the contracts are stored on the blockchain raw, i.e., the way they're written by the developer?
The contracts on chain are stored as a PVM blob.
Nice. And Rada asked the one about people coming onto PVM. So yeah, keep going.
Cool. Okay, what's the roadmap? So now we have Palette Revive on West End, which is our test net. Then Kusama is a production network, a canary network running the same code as Polkadot. We are going to deploy, I think, end of April, and then we expect Q3 to deploy Palette Revive on Polkadot Asset Hub in Q3, and also in Q3 precompiles and the JIT compiler should become available. And yeah, and then we will look forward to what we do with Jam in the further future. So I'll make this very brief. The elevator pitch, what our RISC-V contract stack allows us to do is supporting contracts in any language that are actually fast, and you will be able to pay gas with DOT or stable coins, and we will support the de facto standard Web3 tooling. Like your users can still use MetaMask wallet, for example. Here's a couple links to documentation and support channels. And yeah, that's it for the presentation.
Nice. Do we have other questions? Rada's putting lots of things in chat about how this hackathon is the first platform where we're exposing PVM to a broader developer audience. And that let's second his pitch. This is a chance to play with PVM in its earliest stage. The hackathon is there for you to have that exposure and the opportunity to build things on the new tech. I think that is most of the questions covered. Rada answered the one about wallets, about tooling, the SDK, Substrate and Rust, limitations. Looking pretty good. There is one. Did we answer this? What are the limitations or challenges associated with deploying Solidity smart contracts on Polkadot compared to native Ink contracts? Do you want to answer that?
Sorry, I was distracted.
That's all right. What are the limitations or challenges associated with deploying Solidity smart contracts on Polkadot compared to native ink contracts?
Compared to native ink contracts, what are the challenges? I mean, ideally, there's no further challenges. I mean, we don't really know yet, because I think they are still working on a ink version that is compatible with PolkaVM. And yeah, I guess we will see, hopefully. So if any challenges arise, and it should, if it is easier to deploy Solidity for some reason, then we can fix it for ink, I hope.
Nice. Good. All right. I think that's most of the things then. Cyrill, anything you want to add?
No, I'm good for a quick tech demo.
Yeah, let's do it. Go for it.
And more questions in the end if
Nice.
anything comes up. So I will do two things. First, I will just show deployment with Remix IDE and MetaMask, just to showcase how easy it is to deploy contracts. And then I will show how you can call a Rust contract from a Solidity contract on a local testnet. So the Solidity one is like, it's super easy. So I'm just here on remix.polkadot.io, and I have MetaMask installed. This is the faucet for our testnet. Let's see. I should have some funds left, but just, oh, okay. Okay, I should be good. So it's not very interesting, but just to show, like, we can compile this contract here, and then we can choose. So you would select, you would, of course, hold on. You need to configure and inject the provider. The docs page I linked earlier shows you how to do this and where to find the configuration for the West End test network, which is where we are going to deploy here. And then we can deploy that. I will sign the transaction with MetaMask. And then hopefully the deployment worked. And then I can call my contract here. I can store some number. Of course, I have to sign the transaction again. And then I can see what's in the contract storage. So it seems to work, right? So that's not very interesting. That's just standard functionality. So let's call a Rust contract from Solidity. So I will run. So I'm in the Polkadot SDK directory here. And by the way, this is like all I'm gonna do. Is also in the tutorial, in the documentation I linked. So I will run the node here and the RPC binary, which exposes the RPC interface here. And then I'm here in this Rust contract template folder. So this is the repository you see here, github.com parity tech/Rust contract template. And this contains a Rust contract and a Solidity contract. And the Solidity contract can call the Rust contract. So let's see. We have, so this is this repository. So we have our Rust contract here. And you see it just essentially can calculate a Fibonacci number, right? And what it also can do, it has this function which expects an address for implementing this Rust contract interface, and then it just tries to call this. And so the idea is, so if we look here, here is our Rust contract. And it's not terribly complex. So it's actually not a lot of code. And so you cannot just ignore all of this here. This is some lower level things. The interesting thing is here, the call export is like what's get called when you call the contract. And then you see it reads some input, and then it calculates the Fibonacci number and eventually returns the result. So far, so good. Now you'll have to make you have to do these two. I mean, I already did this, so it should work. And then we have our little contract blob here. So we're gonna do this, and then I will use cost here. So this is Ethereum tooling, right? Oh, okay, I already did this, so we're good. So it deployed the contract, and someone asked whether EVM tooling works for Polkadot. So the answer, as you can see, is like, yes, it does. If your Parachain, in our case, the Polkadot hub or asset hub system chain, like pretends to be an Ethereum chain, then yes, so we are using cost here. And so this works. So by the way, is this big enough? Can you actually read what's on my screen?
Yeah, we can.
Okay, perfect. So now we are, let's see. So we are grabbing the address of that account, and then we are actually gonna call it. So Fibonacci of 4. So let's see. Yeah, so it calculates Fibonacci numbers. Great. So now we have this Solidity contract, right? And now we were going to build this. So the Resol C, our Solidity compiler, also runs in WebAssembly. So there's an npm package which can compile this code. Sometimes it takes a while. And there's also, so the compiler is also available as a native binary, so you can kind of do the same. So this is how you would invoke it. We would just ask it for a binary. This is the output directory. And then we see here our little PVM blob. So I think this tend to just not finish the first time. Okay. So what we're doing now is this file here. So you see, this is a PolkaVM blob, which is the result of compiling this contract to PolkaVM. And we will now deploy that. So it worked, and this is the contract address. And now we can here compare the gas estimates of both. And so what you see here we are estimating the gas cost of calling the Rust contract, and here of the Solidity contract. And I mean, this is not doing a lot of computation, but if we increase that, it should become pretty obvious. So the Rust contract is just much more. So Solidity and the EVM and all this stuff, it's not very efficient and not very optimized for like low-level computation. So this is kind of expected that the Rust contract just uses like much less gas. And now what we can do is, so what this does, this calls the Solidity contract, saying like, please execute this Fibonacci Rust function, and we are passing in the contract address of our Rust code. So what this does is it calculates the Fibonacci number by calling the contract, this little Rust contract here, right? So what I want to show is, like, let's pretend this is not actually doing some Fibonacci, but maybe verifying a CK proof or something that's actually meaningful work. So let's see the gas estimate of the Solidity implementation, calculating 27 numbers. It's like, let's just keep this in mind. But now, if we estimate the same computation of 27 Fibonacci numbers, and here we are still calling the Solidity contract, but ask it to do the actual computation by the Rust contract. So you see, even though there's like one more contract involved in the call stack, and this is also something that's costly to do, calling the Solidity contract to then call the Rust contract to do some number crunching computation is actually a lot cheaper than just implementing it all in Solidity. And what this means is that so it's like, the obvious example is with machine learning. It's kind of the same situation, right? You have like all the Python script just orchestrate like models written in C++. So it's like convenient to write your business logic in Python, or in our case, it's like convenient to write your business logic in Solidity. But libraries like Stark verifiers or hash functions or whatever you need can be implemented in Rust. And then you can still write most of your like user-facing code in Solidity, but call into Rust for a gas optimization. Yeah, that's it. So there's this Polka tool, which has like, so this is just something I can show you. We can disassemble this contract, so you get to see. So this is like, so PolkaVM is like the contract blob as opposed to an EVM blob, and this is all the low level, how it looks like. Okay, so that was it.
Excellent. Cyrill, thank you very much. And I know we're perfectly on time. So what I suggest, everyone, is for additional questions, we take them to the Discord, or as Rado suggests, there's soon going to be a ticketing system on the Polkadot Discord itself. Please go to either places. In the meantime, Cyrill, thank you so much for your time and a very clear and erudite presentation. And I look forward to all the exciting things people will build on the PVM. Is there any final remarks or things you want to mention before we finish up?
Yeah, thanks for having me. I have like 5 more minutes to take any questions if there are any.
There's one about, is there a Polkadot LLM? But I don't think there is, but you could build one in the hackathon, guys. Alberto very nicely answered the question about paying for gas, obviously. Karim says there's an LLM in the working. Very good. That's what we want to hear. Nice. There was a question about, but it was answered about configuring West End in Remix. Radar is typing now as well. Whole Polkadot crew is here. It's great. We talked about wallets. We talked about the SDK. We talked about precompilers and the documentation there. We talked about the Polkadot Hub. Sorry, I'm going back through all the questions now. Bridging between parachains, pretty hard overall. Do you want to answer that? How does one bridge between the parachains? I assume they mean asset bridging more than anything else.
Yes, so this is like with XCM, we can this just works in the general sense, and then we will have contract interfaces. So we will have precompiles supposedly for the XCM palette, and then you can pass arbitrary messages between parachains. How I personally envision this, there will be like much higher level APIs that then take care of the underlying XCM stuff. So you will find a Solidity contract for, let's say, transferring assets between parachains, or some specific parachain could offer a Solidity library that you can deploy to Asset Hub. And then you have a set of functions like, hey, send this asset to this parachain and swap it for like this other asset and send it back. And then all you have to do as a contract dev, you call this, you deploy this contract using this library that this parachain provides, and then you don't have to think about it too much. So this is kind of how I envision this.
Excellent. Good. Question. Any particular new things that are being shipped at the moment that we should be aware of? I assume they've been within the scope of the hackathon, particularly as it pertains to the PVM and Solidity smart contracts. Anything we're all ready to go? Is there any new things that are going to pop up that people should be aware of?
Yeah, the Kusama release is something we look forward, and also we are working on the precompile interfaces right now as we speak, and we expect this to land in the next few weeks. So if you're super curious, like, you should have a look as soon as it's like a preview is available.
Nice.
In Polkadot SDK master branch.
Excellent. Okay, very good. All righty, guys. Thank you very much. Any other questions for Cyrill this evening? Otherwise, we take them to the Discord. Cyrill, thank you so much for your time. We look forward to all the things you're going to build. Tomorrow, guys, we have writing safer substrate and ink contracts. So actually the opposite, which is quite funny. That's at the same time at 5:30. Otherwise, this video will go up tomorrow morning and be available to all of you for your building asynchronously as it comes. Otherwise, guys, thank you very much. Have a good evening. Thank you to everyone in chat and for all the very helpful helpers who handled questions as well. Kareem, Alberto, Rada, thank you very much for your time too. Otherwise, guys, see you later. Enjoy.
Thank you, guys. See ya.